Latent Adversarial Diffusion Distillation, or LADD, is a new method which basically takes a diffusion model and distills it into a model maybe of the same size, maybe of a bigger size, that does larger step sizes. So you can do less steps to get an image of hopefully the same quality. In this case, they train a model, or they distill a model from Stable Diffusion 3 to what they call Stable Diffusion 3 Turbo, and they do this so usually Stable Diffusion takes like 50 steps to get a really, really good image, maybe 30 steps to get a pretty good image, but they make it where they distill this into a model with 4 steps. So it just takes up to 4 steps. It can be 1, 2, 3, or 4 to generate an image, and in 4 steps you get some really good quality. Even if these are cherry-picked, these are still pretty good for a distilled model with 4 steps. So yeah, that's the method, and the idea comes from adversarial diffusion distillation. And the two main things they do differently from that is they bring this to the latent space. They use synthetic data, and a third thing is they combine the teacher and the discriminator into the same model. So real quick, I will go over how diffusion and all that works, and then I will get into the method. So good old diffusion. So if you already know, feel free to skip ahead. This is just normal diffusion stuff. So got your good old cat. There we go. Creepy cat, but that's fine. So you got your cat, and we'll call this x0. So you take some image from your data distribution, and we're going to call this the data at time step 0, and we're calling it x0. And what you do is you add you slightly add a bit of noise to it. Like you just add a little bit of noise, and I'll represent that as these red dots. And this will be, say, t is equal to maybe 0.1, or maybe t is equal to 1. In this case, I'll represent it as t is equal to 0.01 or something like that. And this will be x 0.01. And then you step again. So we step again, and we add a little bit more noise to the image. So here, this would be, say, t is equal to 0.00 or 0.02, x 0.02. And you add a slight more, or you add slightly more noise. And you keep on doing this over and over again until you get to your final image, which is a pure Gaussian, it's just pure Gaussian noise. So you have no more signal and you have 100% noise. And this will be x1 at t is equal to 1. So you could create this chain, and this is the forward process. The forward process is you take an image and you slowly corrupt it by adding noise until you get pure noise. And you can model this as an interpolation. So x at time t is equal to x0, or alpha t x0, plus 1 minus alpha t x1, where x1 is equal to, say, some noise, which is equal to, or which is sampled from a Gaussian with 0 mean unit variance. Usually you can change the variance if you want. So it's an interpolation between signal and noise. And you can get anywhere in this, so it's this continuum. And the way they model this is using something called a flow model, and that just means that you have a straight path between x0 and epsilon. So between this image and this image, you have a linear interpolation between the two. For other methods, you don't have to have a linear interpolation, but this just means that alpha t, or alpha 0, is equal to 1, and alpha 1 is equal to 0. So at time step 0, you have 100% signal, and at time step 1, you have 100% noise. And that's basically, and you can use this, you use this for your flow model. This is just a forward process. Now the backward process is you have your model, say m theta, and m theta learns to reverse this process. So m theta takes a noisy image and it removes the noise from the image, or rather what we do instead is we give some model a noisy image, and what the model will do is it'll predict all the noise in the image. So we give it this image here, And the model is just going to predict, like it'll predict to basically remove the signal like this, and to just give back the noise. And that means that you can just subtract the noise from the image to get the original image back. So all we're doing is we're training a model given some time step and given an image at a time step, xt. It predicts all the noise in the image. And you do that for all steps in your chain. So the way you train this is you sample a random time step, you sample a random image, you noise it to that random time step. Using some random noise you also sample, and you will hopefully have a model that if you train this for long enough, you'll have a really good model that given an image, it'll predict all the noise in the image. Now it's going to have some error. It's going to have, it's not making a perfect prediction. So you actually have to step in this space. And you can kind of think about this as kind of like an ODE, or it is an ODE. That's how you actually model this. So if you have some image in your space, and in this case, it would be a 2-pixel image, X and Y. You just have 2 dimensions, and you have some image here, X1. So this would be, or this will be X0. Your model may make a prediction. You're hoping to head in this direction. This is where your actual image is. Your model may make a prediction in this direction, and you would step in that direction a little bit. Because if you just had a one-step prediction, it would end up over here, which is some, maybe it looks like some image, but it's not going to be what you want. It's not going to look like a good image. So you step in the direction, and your model makes another prediction, and you step in that direction a little bit, and you keep on doing that until you end up at x0. And this is why you have to use an ODE solver. There's still curvature in your space, even though you're using a linear interpolation. So you have to step because there's curvature. And methods to distill models usually try to reduce the curvature a little bit. If you reduce the curvature, you can make larger steps because the space isn't curved as much, so the error you make is a lot less when you take larger step sizes. But that's not what they do in this paper, but that's what they do in, say, LCM, latent, I think that's condition models. I forget what that is, what those are, but you can essentially smooth out the space if you wanted to distill the model, but that's not what they do here. So this is basically diffusion models at a very high level. They use something called flow models, and if you're curious, Yannick has made a really good video about that. I would go check that out. But yeah, what you usually do instead of having it in pixel space is you actually bring this to the latent space. So you have a encoder. Let me take this image up here. So you have this encoder, or you have this image, and you have an encoder here. And this will take it from some image x, y by 3 to some latent representation of that image, which will be c by, or we'll call this big L and big W, and this will be little l and little w. So maybe if this was L equals W is equal to 512, then the little l and little w is equal to maybe 16 or something like that. So it's a massive reduction, and c is maybe 128 or something large. So this is your feature representation of your image. Hopefully it's a very good representation of the image, and in the original Stable Diffusion paper, they add a ton of losses to make this autoencoder work well. But you then have your decoder over here, and the decoder will decode your latents back to the original image, like that. So this middle part here is what you do Stable Diffusion on. You usually, instead of taking an image and then adding noise to the image, you take an image, you then throw it into the latent space, and you add noise to that instead. So you would have your forward process here, which would add noise, and you would train your model to reverse that to get some latents. And you would start off with some noise, and to sample from that, you would throw this through your model, M theta, and this would make some prediction some number of times. It'll spit out the latents that you want, and then you would decode that using your decoder here. Where I can't draw a good D. There you go. So that's your latent diffusion models. So what they want to do is they want to use this method called distillation. And what distillation does is in the normal sense, you have some massive model here. So the massive model takes some data, and it makes some prediction on the data. What you want to do is you want to have a much smaller model, we'll call this the same M hat, which takes the data and makes a very similar prediction, or hopefully the same prediction. And you want this model, which is much smaller, to do the exact same thing as this model. Of course, that's not going to happen because the space this is working in is much smaller than the space the original model is working with, but you're hoping it's still good enough. And this is the normal sense of distillation, and you usually just have a loss to you usually just have mean squared error loss between the predictions. But we don't want to do this. We don't want to make the large model a small model. Rather, what we want to do is we want to basically turn a model that does multiple steps, or we want to make a model that makes a prediction for some, maybe makes a prediction this way to make a better prediction of the step. So in this sense, we can make larger steps. Basically, we want to make it so that we can take less steps with our model. So we're not reducing the size of the model. Rather, we're taking a model that requires a lot of steps and reduce it down to a model that requires a lot less steps to generate images. So that's the idea. Take a model that requires a lot of steps and reduce it down to a model that requires a little, to require a few amount of steps. We're not reducing the model size at all, at least not in any significant way. So they have these diagrams here. I drew out these ones up here. I feel like these are a little hard to understand, but I'm going to walk through these. So the idea is you have a teacher model. The teacher model is usually your big model, and the student model is usually your small model, and you usually want to reduce the size. But in this case, the teacher model is the one that requires a lot of steps, and the student model is the one that requires, or is hopefully going to have a lot less steps. So the way you train this is you have your image here, and actually this is going to be ADD. This is going to be the old approach. We'll talk about the old approach and then the new approach. So the old approach takes an image at time step 0, and this image will be from your data distribution. So you have some data, or your data that you trained Stable Diffusion 3 on, and you sample from that data set, and this will be the image that you're working with. You then have to encode the image because we're working in the latent space. Once you do that, you have your latent representation, and I represent it as a small image, but it's going to be some mess that you won't be able to comprehend it. It looks like noise, but it's not. It's a dense representation of the image features. You then add noise to the latents in 2 separate times, one for the student, one for the teacher. The student will then make a prediction. It'll basically decode this using however many steps you want it to take. And you noise it to a certain time step. So you sample a random time step. Maybe it's 1 being 100% noise, or 0 representing 100% of your signal. And you then decode this. And the student will decode it in a lot less steps. So if you have, say, t is equal to 1, so 100% noise, maybe your teacher model requires 50 steps, but you only allow your student model to do maybe 4 steps or 1 step to basically get the prediction. And you then want to do these, you then want to match the predictions. So you want the image that the teacher produces to be the image that the student produces. And you do that in the pixel space. So you decode both the images, and you now have your image that was decoded by the student, or generated by the student, and the image generated by the teacher. So a lot of steps, a few steps. And you have this distillation loss, which is just your pixel-wise mean squared error between the two. Now, the problem with just having distillation loss is it's a pixel-wise it's pixel matching, so you're not going to end up with a really good image. You're going to end up with this weird looking average. So just having the distillation loss alone isn't good enough because it only does pixel matching. Now, it would be better if you have something that does feature matching, or at least can look at the features and send a gradient signal to tell it how to update the weights for feature representations rather than pixel matching. And to do that, we use a GAN. And you can think of the student as the generator, and we're going to use Dino as the discriminator. So a GAN requires real and fake data. And the fake data, like I said, is going to come from the student model. So this is just our fake data. And the real data is just going to be the images from the data set here. And you just train this where Dino is your discriminator, and you want your student, the discriminator is going to learn to differentiate the real and fake data, and the generator is going to learn how to maximize the fake, or how to make the fake data look as real as possible. Now, I'm guessing these two losses work really well together because, like I said, this is pixel and this is feature, but also GANs are really hard to train because maybe the generator will be too good or the discriminator will be too good, and if one overpowers the other, then usually end in some collapse where that model does a lot better and the other one doesn't learn. But like usually you have your discriminator collapse because the discriminator task is a lot easier than the generator one. But I'm guessing the distillation loss helps a lot to make the GAN training a lot more stable. So these two seem to complement each other. Now, what they do instead of having this methodology all in pixel space, the losses are all in pixel space here. We do this all in the latent space, and this makes it easier because this is not computationally friendly. The reason everything was moved to the latent space in the original Stable Diffusion paper is because doing it in pixel space was not computationally friendly. So move everything to the pixel space. That's the first thing they change. The second thing they change is they only use synthesized data, and that's because humans suck at captioning data. So we only use synthesized data. And the third thing is the teacher is also going to be the discriminator down here. Synthesized data has just been shown in general to be better than human data for training models, which is interesting. So that's something that keeps on popping up. But anyways, we first synthesize some data. So we take some noise. We also take some random caption, so some text, condition the teacher. So the teacher is just Stable Diffusion 3. And we generate a bunch of data. So we generate some data, and this data right here, or this latent representation, will be some latent representation generated by the teacher. And since the teacher works in the latent space, that means we don't have to do any decoding at all. And we also want the student to work in the latent space. Now, just like up here, instead of having to take an image from the dataset and encoding it, we take some synthesized data and we don't have to encode it at all. And that's the start here. So what we do is we add noise separately for the student and the teacher models, and we get predictions for the latent representation of the image for the student and the teacher. And instead of decoding it, we do the pixel-wise distillation loss in the latent space. And this is a lot more computationally friendly because you don't have to encode and decode anything. So this is just done in the latent space. And another nice thing about this loss here is that it's not a pixel-wise loss, it's a feature-wise loss because each part represents a feature. So this may be better than this loss up here. Maybe. Just theorizing about that, but you do this in the latent space. Now, we also have our discriminator in the latent space, and you use the same model. You use Stable Diffusion XL for the discriminator because it also works in the latent space. And your discriminator, or your Stable Diffusion 3 model, is a transformer. And transformers have a bunch of layers, so you basically take your image, you break it out into tokens, and you have a ton of layers. So layer 1, and after layer 1, you're going to get a bunch of activations, and after layer 2, you're going to get more activations, and after however many layers they have in Stable Diffusion 3, you'll end up with your resulting noise. They leverage this multi-layer, these multiple layers by adding a discriminator head to each layer. So if this is your teacher here, you take the real and fake data. So the real data in this case is going to be the one generated by itself, which is kind of weird, but the real data is the one generated by itself, and the fake data is the one generated by the student. And you're going to pass that through all the layers of the teacher. But at every layer, you have a discriminator head. And this discriminator head is going to use the features of that layer to make its classification on whether this is a real or a fake image. So you have a ton of heads, and you have a head for every layer in the teacher, rather than having one at the end of the teacher that makes one classification. And every head will hopefully find different features, allowing the propagated loss or the gradient signal to be a lot more rich with information on how to update this image, because each layer finds different features, and those different features will be used to inform the discriminator how to make its prediction, which will then be propagated to the student via the loss. So, and this in general helps adding multiple discriminators for every using the activations rather than just having one discriminator. So this is what they do. All of it is in the latent space. And yeah, this is basically the method. It's not too bad. You just have your distillation part, your student teacher, and your GAN part. And yeah, that's the method. So there's a few notes I made. I'm going to go through them over here. One thing is that each token sequence, they apply independent discriminator heads. Each discriminator is conditioned on the noise level and pooled clip embeddings. So this is just giving the discriminators more information to work with. They mention here, in one-shot scenarios, CFG simply oversaturates samples rather than improving text alignment. This observation suggests that CFG works best in settings with multiple steps, allowing for corrections of oversaturation issues in most cases. Typo. They mention that CFG does not work well for this few step case. So they train a model using 4 steps, and it doesn't work well. CFG does not. So it seems like CFG only works well for multiple iterations, while it works very poorly if you only have 1 or 2 iterations for your generation. So like CFG couldn't really be applied to GANs because that's a 1-step generation. That's also not how GANs are trained, but using that as an example, it couldn't do that because CFG doesn't work well unless you have multiple steps. They also mention that synthesized data works better than normal data, and they have some results showing that later. What do we have here? So when biasing the distribution towards low noise values, they observe missing global coherence, while textures and local patches look realistic. Lacking global coherence is a common problem in adversarial training, and additional losses such as classifier clip guidance are often introduced to improve image quality. So adding a tiny bit of noise, training a model on a little bit of noise, and training a model on a lot of noise result in different images. So if we only train a model on a distribution where it's mostly, so on a time distribution, this is the time distribution. If we train it where we're mostly at the beginning of the process, so we only had a little bit of noise, what we'll end up with is a model that generates images where the details are really good. So these have really good details, but the quality, the overall structure is very bad. I don't know what the heck's happening over here. On the other side of the spectrum, if you have mostly super high noise levels, then you end up with something that has really good structure. So the image makes sense, but the details are quite poor. So you basically want this trade-off somewhere in the middle where the global features make sense, they look good, while the individual features also look, or well, the individual smaller features also look good. And this is something they work with, or this is something that they fix by adding a scheduler for the noise levels. They start off with low noise levels, and they slowly increase to high noise levels, and they find that works pretty well. And this is the teacher noise distribution. I suppose I forgot to mention that one thing that ADD did not have is you can't control what your discriminator is learning. It'll learn the features in general, but here you can't tell it to learn low noise levels or high noise levels, but here you can. So we add a little bit of noise, I guess, prior to the discriminator over here. So instead of you directly throwing a real or fake image into the discriminator, what we can do is we can add noise to the image and then throw that through the discriminator. So adding no noise will basically have it classify between real or fake images, and having a ton of noise will have it classify between real or fake Gaussian noise. And somewhere in the middle seems to work the best. So you can train your teacher on varying noise levels, and if you add a lot of noise, you basically are teaching your teacher about the more global structure of the images. And if you only add a little bit of noise, then your teacher works really well with the high level or the low level features and the details, as shown over here. So if you train your discriminator on really low noise levels, it'll learn how to. Your student will eventually learn from the discriminator about these details. While if you train it on a lot of noise, the discriminator is going to teach the student about the global structure. So that is an interesting property of LADD that you could not do with the original ADD paper, and that's because of this. Dino v2 doesn't have any idea of noise, while Stable Diffusion 3, as our teacher, does. They also mention that synthetic data improves image text alignment. So the left side is human data, and these look pretty bad. If we look over here, the synthetic data looks a lot better, and they mention if you just have the adversarial objective, it works quite well, but if you add the distillation objective, the details look a little bit better. So adding that helps, and I'm guessing it also helps for stability as well in the GAN loss. They find that it outperforms LCM, so one of the method of reducing curvature, and they also find that the student can be scaled. So hopefully this graph can go up like that. Well, that's what we all wish. It probably stabilizes and somewhere over here and converges over here. The data generator and the teacher, which are just both Stable Diffusion 3, do not really benefit from scale, but it's quite nice that you can benefit from scale because usually GANs don't really benefit from scale. So the generator can, but the discriminator doesn't really in this case. Oh yeah, and how they train this. So they train across different time steps, and this is the time step data, or these are the time steps they train the model on. So they only train it on 4 discrete time steps. And they also mention here how they handle the local details versus the global structure problem. And they say they start with low noise levels, initial probability distribution of p is equal to 0, 0, 0.5, and 0.5. And after 500 iterations, they shift towards full noise to refine single shot performance. So that's what they do to help the model train better. Other than that, I think that is about it. Idea is not that bad. Just throwing a ton of losses at this and making it work really well, just like in the original Stable Diffusion paper. But yes, this is latent adversarial diffusion distillation.